Welcome to 3.2 Differentiability Part 3, which is titled with the main thing that you need to get out of it. Differentiability implies continuity. In order to understand this and really understand what implications mean, we are going to take a step back and first talk about logic. Logic is one of the coolest classes I ever took in college. Yes, I took a class literally called Introduction to Logic, and it was so fun because it was mathematical without being super mathematical, if you know what I mean. And it was like really easy, and it satisfied this extra credit that I had to do without having to like write papers and do all that stuff. So if you're math-minded and like rational thinking, logic is a great class to take. All right, enough about that. We are going to talk about the basics of some logical statements. The most basic logical statement we can make is called if P, then Q. P and Q are just things that could happen. We'll get into an example in a moment. If that original statement is true, if P happens, then Q happens, then that means that if not Q, then not P is also true. This squiggle means not, or like the negation or opposite of. That is called the contrapositive. And the interesting thing about the contrapositive is if your original statement is true, then your contrapositive is also true. Let's look at an example and give P and Q meaning. I have come up with an original statement that is true. If the leaves are changing, then it is autumn. This is an if P, then Q logical statement. If P, then Q. Since this is true, that means its contrapositive would also be true. The contrapositive looks like if not Q, then not P. So if it is not autumn, then the leaves are not changing. That's also a true statement. Because the original statement was true, logically the contrapositive is also true. Logic is the way that you can organize your thoughts, you can organize debates, you can organize, arguments, for lack of a better word, because logical statements just rationally are true if you do it right. So a contrapositive is always true if the original statement is true. Now, what in the world does this have to do with math or calculus specifically? Well, we're going to talk about that if a function is differentiable, then it is continuous at a point or on an interval. Therefore, differentiability of a function implies continuity of that function at a certain point or on a certain interval. That is a logical statement. If differentiable, then continuous. We are also going to talk about the contrapositive also being true. Therefore, if we know something about a function's differentiability or continuity at a certain point, we can make logical, correct assumptions about it at that point as well. Here is our logical statement pertaining to calculus. If a function is differentiable, aka if it has a derivative at x equals a, then the function is continuous at x equals a. Go ahead and pause the video and write down what the contrapositive to this statement would be. That's a good exercise. The contrapositive would be if a function is not continuous at x equals a, then the function does not have a derivative or is not differentiable at that same point. This is only saying that if we are differentiable, then we are continuous. Something about logical statements is that the converse is not true, meaning you can't just switch P and Q around. You couldn't say if a function's continuous, then it's differentiable. That doesn't work. The contrapositive does work. If not Q, then not P. I know this is a lot of logic, but it's a really interesting look at what we can and cannot conclude from knowing certain aspects of a function. Here's an example that we'll take a look at. Off to the side, I just wrote in very kind of broken English, I guess, what we just talked about. So if we're differentiable wherever, then we are continuous. Here's the contrapositive. If we're not continuous wherever, then we're not differentiable at that place. Diff meaning differentiable. Let's just review what continuity means real quick. Continuity means that we do not have to lift up our pointer or whatever we're drawing with at all. So are we continuous along here? Yes, we are. Are we continuous when x is -1? Yes, we are. We're continuous there. Are we continuous all along here? Yep. Are we continuous at x is 2? No. We have to lift up. We have to jump. There's a jump discontinuity here. And then we're continuous all to the right. Okay. So let's talk about making some logical assumptions or conclusions based on what we know. So if we're differentiable at a certain point, then we're continuous there. So are we differentiable when x is -3, let's say? Yeah, sure. We could draw a tangent line here. It would just be this line. So therefore, are we continuous at x is -3? Yeah. How about here at -1? Are we differentiable there? No, we're not. So because this is not true, the antecedent is not true, then we cannot come to any sort of conclusion about continuity here. Now, we know that we're continuous, but this is an interesting point. Only if we're differentiable can we automatically assume that we're continuous. Now, we can look here and see that we're continuous there, but we just can't come to that conclusion using this idea. We're not differentiable here, but we are continuous. It's kind of an interesting idea. This is not always going to help us. If we look here, we're not differentiable at x equals -1, but we don't have anything that says if we're not differentiable. So we really can't come to any sort of conclusion there. Now, we can because this is actually drawn and we can see it, but if we didn't have the function drawn, we couldn't come to any sort of conclusion at x is -1 if we didn't know the function. Let's take a look at x is 2. We are not continuous at x is 2. If we're not continuous, then we're automatically not differentiable. Because we're not continuous at x equals 2, we can come to the conclusion that we're not differentiable at x is 2. Let's go through some questions. We have some function, and it's differentiable at x equals 3. We're told that. We want to know, is f of x continuous at x equals 3? Well, we know that if we're differentiable, then we're continuous. Therefore, we would say yes, because differentiability implies continuity. In this next question, well, we're actually given a statement first. Some f of x is continuous at x equals -1. Is f of x differentiable at x equals -1? Well, we don't know. We don't have if continuous at all. We can't just flip this around. That's called the converse. And so if continuous then differentiable, that's not always true. Therefore, we could be continuous somewhere, but not be differentiable. An example being at a corner or a cusp. So I'll draw that real quick. Here's a scenario in which our function's continuous at x equals -1. Some piecewise function. Our function's continuous when x is -1, but it's not differentiable there. If we zoomed in at this point, we would never see a line. It's not locally linear. The derivative from the left and from the right never quite match up. So because it's a corner, or I could have also drawn a cusp, we're not necessarily differentiable at x equals -1. But we could be. I'll draw a situation where we could be. So here's a situation where we're continuous at x is -1. Just some quadratic function, some parabola. It's continuous at x is -1, and it's also differentiable there. However, just because we're continuous at a point does not necessarily mean we're differentiable. As I just drew before the blue piecewise function, it could be a corner. So how do we answer this question? We answer it with a maybe. Is it necessarily differentiable there? Continuity does not necessarily imply differentiability. So we might be differentiable there, we might not be. This next one says, a function f of x has a jump discontinuity at x equals 2. Is f of x differentiable there? Well, that means it's not continuous. It has a discontinuity there. If a function is not continuous, then it is not differentiable. Therefore, because it's not continuous at x equals 2, it is not differentiable at x equals 2. So we would say no. I can draw this real quick. A jump discontinuity at x equals 2. Well, I'm really impressed with those lines that I just drew right there. Just going to toot my own horn for a second. A jump discontinuity could look like a lot of things, but I'll just draw it like this. Could look like this, some piecewise. And no matter how much we zoom in when x is 2, it's never going to be like a nice straight line or anything. We clearly have this big gap here. So when we're discontinuous or not continuous, then we're not differentiable. Here's the main idea. If we're differentiable, then we're continuous. It does not go the reverse of that. You can't say if you're continuous, then you're differentiable. That's called the converse of a statement, just flipping it around. That is not necessarily true. It might be, but it does not imply truth. We can, however, use the contrapositive of a statement, and it will be also true if the original statement's true. If we're not continuous at a point on our function, then we are automatically not differentiable there. I know this is very much like shorthand, but this is a great thing to write in your notes. You could just write out differentiable here, but this is the main gist. And if you cannot, if you don't know about differentiability, or if you don't know that you're discontinuous, then you cannot automatically make any assumptions on the outcome. So I hope you enjoyed that little dive into some logic here. You learned what a contrapositive is to a statement, and that it is always true if your original statement's true. We also learned the converse is just flipping something around, and it's not necessarily always true.